Hi, Mr. T here. This video is going to look at electronegativity, the periodic trend electronegativity, and how we can explain the difference in electronegativity between two atoms across a period and two atoms down groups, and therefore how we can answer questions that might turn up in Level 3 NCEA Chemistry 3.4 Achievement Standard 91390. Now this is true for anybody who wants to understand properties of electronegativity. I'll go through the general principles in this video. So generally what we need to remember about electronegativity is as we go across to the right of the periodic table and as we go upwards towards the periodic table, we get more electronegative, the atoms do. But we have to exclude all the atoms that are in group 18, the noble gases, because they do not form bonds with other atoms. They cannot have an attraction to a bonding pair of electrons, therefore their electronegativity can't be measured. So we ignore everything in this last column, and fluorine is in fact the most electronegative atom. So that's the general rule. Let's see how we actually come up with this general rule. So the first thing is electronegativity is a measure of how much an atom can attract a bonding pair of electrons. Sorry, not so how much an atom can, how much the nucleus of an atom can attract a bonding pair of electrons when it's bonded to another atom in a molecule. So what do I mean by this? Okay, so if we have two atoms bonded together, here's a hydrogen and a chlorine, they will share a pair of electrons between them. The electrons will not spend their time equally around each atom. One atom might have more of a share of the electron's time because it has an extra electronegativity, and actually chlorine does compared to hydrogen. Now the consequences of this is that the chlorine will have a dipole moment of delta negative and the hydrogen will have a dipole moment of delta positive. This produces a bond dipole, and bond dipoles can have effects like changing the ability of how molecules interact with other substances in the world. Will they dissolve in water? Can they be deflected by electrostatic charges? Can they be used to dissolve ionic compounds? So these are actually important to know what types of molecules have bond dipoles, and that's directly influenced by a difference in electronegativity between two atoms. Okay, so let's have a look at electronegativity. So if we go down a group from fluorine to bromine, so fluorine has an electronegativity of 4. If we go down, chlorine has electronegativity of 3.2, and then bromine has electronegativity of 3. So we can see generally as we go down, the electronegativity decreases. But why does this happen? Well, the major reason for this is every step downwards we add an extra energy level of electrons. Fluorine has 2 energy levels, chlorine has 3 energy levels, and bromine has 4. So the nucleus in fluorine, when it's attracting, having an attraction to the bonding electrons, let's say fluorine was bonded to a hydrogen, it's attracted to the shared electrons. It's only got one energy level between itself and the electrons it's attracting, so there's only one energy level that can produce some shielding, and the energy level that it's attracting is only 2 levels out. It's not too far, so it's actually going to have a strong electrostatic attraction. When we go down to chlorine, we have 3 energy levels, so the chlorine nucleus is trying to attract the bonding electrons that are in the 3rd level. The valence level is the 3rd level, so it's got 2 levels of shielding between the nucleus and the valence level, so it's got more shielding. And because we have a 3rd level, it's further away from the nucleus, so that also increases the decreases electrostatic attraction. So electrostatic attraction decreased as we go down by 2 general aspects. The first is there is more shielding the more energy levels you have, because there are more electron levels in between the bonding electrons in the nucleus, and the valence electrons that the bonding pair is part of are further away because there are more energy levels. So that's why as we go down a group, the electronegativity decreases. What about if we go across a period? Well, if we go across a period, let's have a look at these four here: chlorine, nitrogen, oxygen, and fluorine. Sorry, carbon, nitrogen, oxygen, and fluorine. Carbon has electronegativity of 2.6, nitrogen 3, oxygen 3.4, and fluorine 4.0. So we can't use the electron level argument here, because all 3 or 4 of these atoms have electrons in the same level. That is the second level. The valence electrons are on the second level. So their bonding electrons, the electron that they share with the atom they're bonded with, is in the valence level. So because they're all the same valence level, they have the same amount of shielding. Only one level, you know, beneath it that they get shielded from, but they all have the same shielding, and they're all the same number of valence electrons away from the nucleus. So what we talk about here is it's the nuclear charge. So as we go across, the nuclear charge increases. Therefore, the attraction from the nucleus to the bonding pair of electrons is stronger because you have more protons in fluorine compared to carbon. So, summary: electronegativity increases across a period and decreases down a group. Energy levels are important when we go down a group. There are two factors that decrease the electronegativity. There is more shielding as we go down a group because there are more energy levels, and the distance is further away because there are more energy levels. Nuclear charge, as we go across a period, as we go across, the nuclear charge increases because there are more protons, so there's a stronger attraction from the nucleus to the bonding electrons. That's why that increases. So